Hello everyone. So in this lecture, we will look at the compile flow. The flow which is compile is a command in Zen compiler that actually carries out synthesis. We will look at what this compile command does. We will look at a few strategies of doing synthesis. We will look at some of the options of compile command. So let's go through the flow again. So we looked at in the last lecture. We looked at how to set the design constraints. So we were looking at this part. We saw design rule constraints: max function, max fan out, max capacitance. Then we saw how to constrain the design properly. That is, how to define a clock. So just to review, the tool will break down all the timing paths into path groups, so that the timing path groups are register to register paths, which are constrained by just defining the clock. There are input register paths which need set input delay to properly constrained, and again register to output paths we need to set output delay. There is a set max area constraint to set area goals. So till this point, before selecting the compile strategy, we have looked how to specify the boundary conditions. First, how to set the library, read the RTL, set the operating conditions, load model, etc. Set design constraints. So before this point, we have not actually performed any synthesis. We are just setting our tool, setting up the constraints, setting up all the desiring operating conditions before the synthesis even goes ahead. Now, the first step of doing synthesis, I mean, after all this is done, after we have gone through the constraints part, the first step is we should know what strategy we want to follow. So I'll talk about the top down and bottom up in more detail in the coming slides. Then we'll go ahead and synthesize the design. The last part is what we'll look in the next lecture is how to check, how to report. So now the synthesis is done. Now there's a lot of checking we need to do to make sure that synthesis is perfect. We need to check the area report. We need to check the resource usage report. We need to check the constraints, whether the goals are being met or not. In the next lecture, we will concentrate on the analyzing and resolving the known problems, how to report timing, how to report area, and so on. So let's focus on the compile in this lecture. So the optimization process DC performs is divided. It's at 3 levels. So DC will do optimization at 3 levels, starting right from the RTM. So first level is called architectural optimization. Second is called logic level optimization. Third is called gate level optimization. Let's look at each of them in a bit more detail. So the architectural optimization works directly on the SDL description. It will include a lot of high-level synthesis tasks such as resource sharing, so sharing common step expressions and resource sharing. These two will result into lower area obviously, because let's say you have multiple adders in your design, in your RTL description. Now, just by looking at a plus sign, DC will know that this will translate into an adder. This is irrespective of any technology that we use. So the things haven't gone to the technology level yet. We are still working at technology independent, that is at the GTech level still. So, but even at the GTech level, PC knows that you are using different types of adders, maybe a full adder or a half adder, and then it will try to find out whether these adders can be shared across expressions or not. So this is what it does in these first 2 steps. It will see if it can share common sub expression, If it can share resources, resources can be data paths like adders, multipliers, and so on. It will also make decisions about what designer components, what designer implementations to pick up. For example, for an adder, there are multiple implementations like a ripple adder, a carry look ahead adder, and so on. So it will do some sort of implementation selection. So when we say implementation means the designer component would be an adder, and the implementation can be one of ripple, carry look ahead, carry save, and so on. Reordering of operations to make sure that the area is minimal. Identifying arithmetic expression for data path synthesis. Now, few of these things like selecting designer implementations and identifying arithmetic expressions for data path synthesis, these options are available only in DC Ultra. What it means is that there are two commands for synthesis. One is compile, which is the basic compile command. Other is the compile underscore ultra command. Compile underscore ultra command is part of a license which is called DC Ultra. I'm not very sure whether it's available for you in the labs. Even if it is not available, it's not a big problem. Most of the trial designs that we look, most of the simple designs that we look are the compile command is good enough for this. So earlier, a few years back, there used to be a separate feature of design compiler which used to help us in doing data path synthesis. Data path means a design which is heavily using arithmetic operations, like an arithmetic logic unit of a CPU, that is adders, multipliers, subtractors, and so on. So DC had a separate feature which was helpful in optimizing this part of the design effectively. Now all those features are now brought into, they are available in Compile Ultra. So Compile does a good job, Compile Ultra does an excellent job on this data path operation. So few of these features are not available in Compile, they are available in Compile Ultra. So except for design and implementation, all these tasks occur only during the optimization of an unmapped design. This is the important part here, unmapped design. What unmapped means is that still at this level, DC has not started selecting the technology that we said yet. We are working still at the GTech level. The mapping has not occurred. For design, a netlist that consists of GTech part is called unmapped netlist. A netlist that is mapped into has already selected the technology library standard cells is called a mapped netlist. So all of these optimizations still work at the unmapped level. However, DC might do some changes to the design implementation even at the gate level stage, even at the mapped netlist stage. Apart from those, all these steps, all these optimization processes run at the GTech stage. High level synthesis tasks are based on the constraints on SDL coding style. We have seen that we can force resource sharing, how we can force resource sharing at the RTL stage itself. Obviously, our constraints will determine what designer implementation is selected. For example, if we have a very relaxed set of constraints, very slow clock, then DC will use ripple adders because they are lower in area, but they are again slow. If let's say our constraints are very aggressive, then DC will not use ripple adders. It will use some other type of adders like carry look ahead or carry save that are better in performance and so on. So after this high level optimization takes place, the netlist we get is the GTech netlist. Second level of optimization is the logic level optimization. Again, this also works on the GTech netlist. Now it consists of the two processes. Let's look in the reverse order. Let's look at the flattening process. In flattening, what DC will do, it will pick up a combinational circuit, pick up a combinational design, and it will represent it using a two-level sum of product expression. So if you go back to your Boolean algebra. Any function can be represented in sum of products form, right? When I say sum of product forms, I mean the unreduced sum of products. So, for example, let's say you have a function which has three inputs A, B, and C, and you have so a three input function will have 8 states, and that function, let's say, for 5 of those states, so that total in total 8 states ranging from 0, 0, 0 to 1, 1, 1, and out of those five states, the output is 1. Now the sum of expression will now contain the unreduced sum of expression will now contain five expressions. For example, it will have A, B, C plus A complement, B complement, C plus something like that, right? Now you could further use Boolean algebra to reduce this, but what DC does is it will use during the flattening process. It will use the two-level sum of product expression without reducing it. What it does, this is carried out independently of constraints, and it is very useful for speed optimization for high performance circuits. Why? Because there are just two levels of logic between input and output, although the area is more. So for timing critical parts where you have such combination expressions, DC will use this process to make sure that there are minimal levels of logic between input and output, so that the speed is of a primary importance here and the area is more correspondingly. Now, as opposed to flattening, DC will use structuring now to reduce this sum of products into something which is more optimized based on the area. So the process of structuring will add intermediate variables. So when we reduce this sum of product expression, we get intermediate variables and logic structures. So it will add those intermediate variables which can result into reduced design area. Structuring is again constraint based. So now see, flattening is independent of constraint and structuring is constraint based. Why? Because DC will only do the structuring for the parts of the design that are not timing critical. For the parts of the design, DC feels that if DC knows that okay, I can reduce the area without affecting the timing, it will do it. So if you notice, the major part of the design will be structured. It will not be flattened. Why? Because for almost all the designs, majority of the timing parts are not non-critical. There are few let's say 5% of the parts will be timing critical. 95% will not be timing critical. All those 95% will get the advantage of structuring. So during this process, DC will search for sub-functions that can be factored out. It will evaluate those factors based on the size of the factor, the number of times the factor appears. So it will factor out the expressions. It will also see whether these expressions, these factors can be reused. So DC will turn the sub-function that most reduce the logic into intermediate variables, and it will factor them out. Although the language here is a bit complex, but the process is exactly same as the one you use to reduce the expressions using Boolean arithmetic on paper. Let's look at the third stage of optimization, which is called the gate level optimization. Now, gate level optimization works on the GTEC netlist to produce a technology specific netlist. Now, why does so DC already optimize a lot of stuff in GTEC. Now, when it goes to picking up the cells, now it will do some kind of optimization depending on what kind of technology library we're using. So first of all, it will just try and map stuff. So it will map all sequential logic input blocks. It will map AND gates, NAND gates, OR gates, NOR gates, and so on. from the cells, it will pick up cells from the target library. Then it will go on to do delay optimization. The goal here is to fix the setup violation, and this part does not fix design rules. Next, it will come to design rule fixing. Now here, DC will try and fix all the design rules, even if it sees a timing violation. So what it means is that although the design rule fixing as an optimization step comes after delay optimization, but as we have we saw in the earlier lecture, design rule fixing takes higher priority. DC will try and fix all the design rules even if it means violating the timing constraint. The last of the goal is the area goal. It is to make sure that the area is met after all these steps have gone through. But there will be a step called area recovery where on a design which is already design rules are fixed, let's say already meets timing goals, DC will try and recover area. But in the process of area recovery, it will not violate either design rule or delay optimization goals. So this just restates the priority of optimization that DC uses. Now, so we saw different levels of optimization. Now let's see what are the different compile strategies available to us. So there are two basic compile strategies. One is called the top-down compile. Second is called the bottom-up compile, and one could use a mixture of both of these, which is actually used mostly in industry. It's called the mixed compile. Top-down compile, as the name suggests, starts from a top-level design. So all the parts of the design, all the different RTL files are read in, and there's only one compile stage. Here DC will attempt to synthesize complete design in one go. The bottom-up compile again makes use of divide and conquer approach, where it's up to us to choose what designs we want, what sub-designs we want to compile first, and then we will use these compile designs and do a top level compile. So mixed compile again uses both of the features of both the strategies. Let's see in detail. We will see few compile scripts also. So let's take one example of a design where, so your design is called top. This is the top level RTL file, top.v. It contains two instances. U1 is an instance of design U. U2 is an instance of design B. Design B in turn contains instance U3, module C, instance U4, module D, instance U5, module E. Operating condition, we have selected worst case, which is expected. We have selected a wire load model 20x20. We are targeting a clock frequency of 40 MHz. So here, let's not be too concerned about what the input-output ports of this design are. Assume there is a clock. Assume there are a number of inputs and a number of outputs. So for all inputs, we are targeting an input delay time of 3 nanoseconds. We are targeting an output delay time of 2 minutes. We are targeting an input drive strength. So now please note, input drive strength and output load are environment conditions, and now the pilot model and operating conditions. So input drive strength, we are targeting. There is a cell called buffer called IV. We are targeting that all inputs will be driven by. We are assuming that all inputs will be driven by this buffer IV. We are targeting to synthesize for an output load of 1.5 power. Now the first step is to develop the environment constraints and at first we will start and develop the constraints for the top level design. Let's look at the top down compile first. So we are assuming that all these RTL files are written at the same time, and the compile command is issued at the top level. So we will set the current design to the top and issue a compile command. Before that, we need to make sure that we read libraries correctly. We set the environment constraints and the design constraints, which is defined by these specifications. So let's look at the script. So the first two commands, first command sets the operating condition, second command sets the Y load model. We set the driving cell to be this buffer IV, which is written in the specification. All inputs, so design compiler, prime time, all such tools use TCL language as their base. So all the commands here, all the expressions here will article expression. So if you do not know tickle at present, you will learn during this course. You will learn how to use as and when you practice working on design compiler in prime time. You will come to know of the various expressions being used, various commands being used in tickle. I would suggest reading some basic material of tickle before attending the labs. It will make the understanding a bit easier. So first two set the operating condition and Y load model. The last two set the driving cell. Let's not look at the set drive for now. This one will set the load for all outputs. So all inputs and all outputs are collections. So when we use this with square braces, this collection will return an array of a collection of all the inputs, all the input ports of the design. Similarly, all outputs will return a collection of all the output ports of the design. So these the ones marked in blue are the environment conditions. We set the environment conditions. We set the operating condition, Y load, input conditions, that is driving cell, and the output. The last one set drive 0. Okay, let's look at the create, and then we come to the timing constraint. Since the target frequency is 40 MHz, we create a clock. We create a clock of 25 ns period. So period is 25 nanoseconds here. One can ask that how do we define the units? Just go back to the library slides and see that the units are defined in the library itself. So usually it's nanoseconds. So period is 25 nanoseconds. The port, the input port is clock here. So assuming there's an input port called CLK, a clock CLK is created at that port. We set the input delay to be 3 as written in the specification. Input delay is always with respect to some clock. Here there is only one clock, CLK. Now here this line tells the DC that I want to set this input delay on all inputs except clock, except the input CLK. It does not make sense since CLK is the point where we create a clock. It is not correct to set an input delay there, and CLK is also an input port. So the command all inputs will return a collection of all inputs. Remove from collection will remove the port clock. It will remove the port clock from the collection all inputs. So this is how we. So this is a very standard sort of command to apply input delays. If you want to have a single input delay for all the inputs, you must be careful to remove the port on which you are creating the clock from this list. Set output delay is simple again. Set output delay of 2 again with respect to the clock CLK on all the outputs. So this is the constraint file in which we have defined all the environment conditions plus all the timing constraints. Now usually it's advisable not to do any design rule fixing on the clock. Why? Because clock usually fans out to almost all the registers in the design. Right? So let's say you have a single clock and you have 1000 registers, 1000 clocks. So this port clock will be driving. It will have a fan out of 1000. So it will have a big design rule violation. A port which is driving 1000 cells. But design compiler is not the tool to fix those. Usually this fixing happens during physical design when an actual clock tree is built. That is why we should make sure that DC should not fix anything on the clock network. This command tells DC to do exactly that. It is telling DC that the drive is 0 on the clock. That means the clock port has an infinite drive strength. So please do not fix it. In the newer versions of the design compiler, there is no need to give this command. There is no need. You can choose to ignore this. A create clock command itself will imply that DC will not touch the port which has a clock defined on it. So such type of networks, the clock network, the reset network, which have high fan out, and which we know that a tree would be built in physical design, high fan out tree it is called. We want to exclude such nets from design rule fixing, and these nets are called ideal networks. So you could use a command called set ideal network on these nets. As and when you work on the designs, you will know all these things. So there's a command called set ideal network which you can use to specify such nets. But please remember, for the newer versions of design compiler, it is not needed to explicitly set an ideal network or a set drive on a clock network. DC, as soon as you give create clock, DC will assume it's an ideal network. Right? So this is the command file which will tell DC what are the environment conditions and what are the timing constraints. Now let's look at the process of top-down compile. Top-down compile is very simple. It's just one compile command. The flow is you read in the entire design, apply the constraints and compile the design. There is, however, one negative point. If the design is big and memory and CPU intensive, it will take a large amount of time for DC to compile. In my experience, I have seen few blocks that are so big and so complex that if you perform a top level compile on those, it takes multiple days for the compile command to run. Now you do not want that, because even if you have a small problem to fix and the design takes, let's say, a day to compile, then if I issue a command now, I will know only tomorrow what the problem is. So you will waste a large amount of time in debugging such kind of design. So it is not desirable to have too large a design go through top-down compile. However, in your labs and all, ideally you would use top-down compile because it is very simple compared to the we'll see the bottom up approach, which is slightly more complex. It is very simple. You don't have to worry about interblock dependencies. So let's say a design like this, you don't have to worry about the interface between U1 and U2, how to constrain this, because the compile is happening from the top level. So in your labs, you would mostly do a top-down compile, but if you get time, then you should try a bottom-up compile at least once, just to understand the flow. So let's look at top-down compile script. Read in the design, read in all the Verilog files. It's a good practice to have one module per file, which is being followed here. So module A is into A.P, module B is into B.P. So we read all the Verilog files, we read the top.p. Please note this script is using read Verilog. You could use analyze elaborate. I would suggest using analyze elaborate. That's the recommendation, because it gives a much more the analyze elaborate combination will give much more insight into the design exploration, right? So you can view all the warnings easily and so on. It sets the current design to top and performs a link command. Now what link command does, this command will try and see if there is any type of logic in your design for which it does not find a module level description. For example, if you forgot to read in design E.P, then the link command will tell you that there is an instance of some module E for which it is not able to find a description. So link is the one that actually will tell you if you have any module description missing. Right? Assuming you read in all the files correctly, you source the constraint file. So this defaults.conf is nothing but this file we are talking about. So, and assume that the libraries and all are correctly set up in the dot synopsis DC setup. So as soon as we invoke DC, the search path and link path are already set. We read in the design, we set the current design to be top, we link the design to make sure that it elaborates perfectly, we source the constraint file. Now we do a compile. We can do compile instead of compile ultra. So what we did is we just followed this flow. The libraries are part of source dot synopsis setup, that is the link library and target library set up correctly. We read in the design, we define the design environment, we set the design constraints, and now we are applying the compile. We selected the compile strategy to be top down. Now we are using either compile or compile ultra. So we use compile or compile ultra. This will compile the design. So as you see, the top down approach is very simple. You can just take the flowchart. You should just know the commands. So actually you can use this script, this complete script, as the starting point. So you can, from the slides, you can copy the script and use it to make your own top down compile script for your own design. You have to just replace read verilog here by, let's say, analyze command for all your RTL. Set the current design to be top, elaborate the design, and do whatever you want to do. Now let's look at the bottom up compile. The bottom up compile is used for big designs where you do not want to compile the design in one go because it takes a lot of amount of time and memory. The advantages are clear that it will you can use divide and conquer approach. It requires less memory than top down compile. It allows time budgeting. I would say this is an advantage as well as disadvantage, because time budgeting itself requires some effort. We'll see what time budgeting is. The bottom up compile, though, on the other hand, it might need multiple iterations to get it to work. Why? We'll see. So in the bottom up strategy, it needs manual revision control. The revision control here is in the context of that you have to make sure that since you have different iterations, so for each of the iterations you have to store the constraint file. You have to make sure that there is some kind of revision control in process so that you know what changes from one release to another. So the idea is in bottom up that first we choose lower levels, the smaller designs, the smaller sub designs, and compile them. Then we read this compiled design as part of the top level design, and now we compile the top level design and applying the top level constraints, and we check for violations. Now the effort from design compiler's point of view is reduced because inside your top level design all the sub designs are already compiled. They are pre-compiled. So what it's doing at the top level is just compiling the glue logic. It's just synthesizing the glue logic. So the effort is reduced. Now it is possible that doing this after you compile the top level, you see that there are no design violations, so everything is fine. This is the most desirable outcome, but usually it will not happen for complex designs or for designs with high performance. It won't happen. So you have to go and perform one more iteration at least to make sure that the violations are removed. How to do that? Let's see. So the first part of the flow is we have to develop. So any design that goes through compile or synthesis. So compile and synthesis are two terms I'll keep on using interchangeably. So any block we synthesize must have a constraint file. Everybody should agree with this, right? Because without the constraint files there are no goals. Without the goals, the synthesis does not make sense. So we have to develop both a default constraint file for the top level and a sub-design specific constraint file. So the default constraint file here will include the global constraints such as clock information and drive and load estimates. That means it will contain all the environment conditions. The sub-design specific constraint file, now they will reflect the time budgeting. For example, let's look at this figure in there. Now here, if I want to do a bottom up, complete bottom up, I have to compile A, C, D and E separately. So when I compile, for example, when I compile the design C, I know the clock, assuming that the same clock comes here. So assume there is a port called CLK. Now this CLK will go to C, it will go to D, it will go to E, it will go to A. The clock is okay, is the simpler part, but now C will have some inputs, it will have some outputs. It will have some inputs coming from, let's say, A, or it has some outputs going to B, or vice versa. Now we need to find the input delay and output delay for these ports. Now input delay of 3 and 2, input and output delay of 3 and 2 at the top level do not mean that same values will apply at C, because we do not know what C's interface to D or to A or to any other block is, right? So we have to study, we have to know what C does actually, and we have to allocate some time budget for the input and output ports of C. This is called time budgeting. So let's say there's an interface between C and D. Now we have to see what, let's say, so there's a register in C which drives a register in D, and there's some combination logic in between distributed between C and D. Now we have to know what part of that combination logic is in C and what part of this combination logic is in D, and according to that we will do some kind of time budgeting. We will define input and output. Now obviously this is not an easy thing to do for a big design which has lot of sub design. So what we do is, at first we start with some gross estimates. So for this exercise, let's assume that this input and output delay are applicable for each of the subdesigns. So we use these values for every design here, just to make things simpler. So we compile the subdesigns. So this is the way we will form the subdesign constraints. We'll compile the subdesign independently. Then we will read the top level design and any compiled subdesigns not already in memory. This is just to say that because we use remove design commands a lot in this process, so we have to make sure that all the designs are read before the top level design is read. We will set the current design to top level. We have to link and apply the top level constraints. If the design meets its constraints, we are done. What if it does not? Then comes the second iteration. Now we apply a command called characterize to the cell instance with the worst violation. Now let's say if we do not meet the timing constraint, we find out what is the cell with worst violation and we apply the characterize command. Characterize command now, so the first iteration has already taken place. Design compiler has all the memory, all the designs in the memory. It knows the interface between all the sub designs. So now the characterize command will enable DC to extract the input output delay, for example, for each of the sub designs, and we can use the write script command to write these values. So write script, when we write out a script using characterize command, DC will write out, let's say I write out a for design C, I write out a script command. I say write script for this design after issuing the characterize command. So what DC will do, it will write out the input delays, output delays, clock information, while load model, operating conditions, and so on. The input driving conditions, the output load conditions, because DC has the information about each of these subdesigns. So it will write out all the constraint, the complete constraint file for us. Now in the second iteration, we have to use this constraint file and resynthesize it. Why? Because the first constraint file that we formed was just an extension. The second iteration has much more accurate values, and it will mostly result into a better synthesized netlist. So we use this script. We read in the remove design online, so just tells that you need to remove all the previous design, which is logical. Again, we read in the RTL design. So we have to recompile from RTL. It will result into a better optimization. We set the current design to this characterized sub design and recompile using the saved script of the characterization data. We have to do this for all the sub designs that fail timing, right? This is the script. So it again uses a tickle construct, so they are not too difficult to understand. They are much like Perl or somewhat like C. So here we saw there are 5 designs A, B, C, D, E. Now the idea is, this is the comment. The idea is to compile. This is the first iteration. We are compiling each subblock independently. This is a for each which will run through all these blocks. This is a for. This is a for loop. Nothing different than a for loop. So for each block in all blocks, we read in the block source. So we set the variable block source. We read this file. We set the current design to this block. We link. We store the default constraints because, as I told you before, we are using the same set of constraints to start with. So whatever the constraints are at top level, we are using for each of the subdesigns. So input output delays remain same, the clock remains same. This is the first estimate. So we source this block constraint, block script. So there can be separate block level constraints which you can form for subdesigns. You could read them here. So we read the default constraints and we read the subdesign specific constraints you might have here, and then we do a compile. So this whole construct here, this complete construct here is doing the first iteration. That is, it is compiling all these small subdesigns. Now we go ahead and read the top level design, set the current design to be top, we link, and we write. We write out the first part. Now, why did not we use a compile command here? It is assuming that top level does not contain any zeros. The top level is just a structural format. That means the top level is nothing but it contains the module instances and wires, which is a very good assumption. The idea is that there should not be any zeros at the top. So the compile effort is saved. There is no need to compile anything at the top level because all the subdesigns are already compiled. The write command will write out a DDC format. DDC is a binary format. You can also write a verilog format. So we write out the first pass DDC. Now we apply the constraints at the top level constraints, and we check the timing. This is for checking the violations. So what this part is doing, this first slide is doing, it is compiling all the subdesigns. It is reading the top level, and it is applying the top level constraint. Now applying the top level constraints do not mean you have to go through the synthesis. Why? Because the top level, the design is already compiled. It is available in netlist format. We just want to check. The only thing we want to do here is we just want to check if the top level design meets timing. So we check for timing violations. If there are no timing violations, done. We are good. But what if there are timing violations? This is the second part of the script. So now we select all instances and we use a characterize command. We tell DC that characterize all these instances for me. Yeah. So now for each of the blocks, for each of the blocks we set the current design and we write this script. This write script will only work after characterize has been done, and characterize may take some time. We are telling DC that characterize all these instances. That means find out what the constraints are for each of these instances. What are the environment conditions for each of these instances? DC will do that, and then for each of the block we write out the script. Now what we have to do? We have to do a second pass compile. Now for each of the block we clear memory, we read in the verilog, here, we set the current design to be this block, we apply the default constraints. Now these default constraints are not timing constraints. In this case they are simply we are setting the operating condition and we are setting the variable. We are not setting the input output delay. Now we read the script that is written out by me after first pass. We are sourcing it here. It is very suitable. There might be any block level specific constraints. We will see in unit 5 what they could be, unit 4 and 5. These might be some timing exceptions, something like that. We source it here and then we compile this block again. So this is the second pass. So the first pass was with estimated constraints. The second pass is with characterized constraints. Now the last part of it is exactly same as this. We will read the top level design, we'll link, we'll source the top level constraints, and we'll check time. We'll check for violations. So we see that a bottom up is comparatively a bit more complex than the top down approach. So my recommendation, if you can do top down, if it is well within the limits of the CPU time and the memory usage, please go ahead. Don't even think about doing bottom up. Top down is much better in terms of area and timing optimization if the design is not large, not too large. So in fact we do chip level like this. Let's say our chip has multiple blocks. Let's say one is USB, other is let's say a CPU, third block can be an impact decoder. So what we do is a USB, a CPU and an impact decoder individually are very big blocks. We cannot synthesize this from top down. What we do is we synthesize USB separately, we synthesize CPU separately, we synthesize impact decoder separately, and then we do top level synthesis. So at a USB level or a CPU level or an impact decoder level, it is a top down synthesis. But at a chip level it's bottom up synthesis, meaning that USB is synthesized already, CPU synthesized already, impact decoder is synthesized already. We just read in these netlists at the top level and do a top level compile, assuming that the top level will have some glue logic in our case. So similarly you could also have a mixed level compile where we take the advantages of both top down and bottom up. So use top down for small blocks, use bottom up to tie small hierarchies into larger blocks. This is one example. For example, a bottom up compile can be used for B, and A, B, C and D are all bottom up compile. For example, that means A is compiled separately, B is compiled separately, C is compiled separately, D is compiled separately. But we define timing budgets for A, B, C and D so that the top level can be read in after reading the netlist for A, B, C and D. If we look from the top, it's bottom up. If we look from the A level of B, it's top down. So these are just some terms. So it's almost always a mixed level strategy for chip level. But for your block, practically, please use, the recommendation is to use top down. Now let's look at what happens when you have multiple instances in your design. So in a hierarchical design, often there are multiple instances of same module. For example, in this top design, U3 and U4 both belong to the module C. So there are two instances of C, one is U3, other is U4. So what are the loaded designs in memory? A, instance U1, C, instance U3, U4, D, instance U5, and B, instance U2. How do we resolve this? Now, the first thing you should understand is that although U3 and U4 they belong to the same module C, the environment conditions of U3 and U4 are different. Why? Here U4 might talk to U5 and might talk to U1. This U3 might talk to only U4 alone. So although the module level remains same, the description remains same. Let's say you have an adder design. Let's say you designed an 8-bit adder. Now this 8-bit adder, although it has the same module, you might have multiple instances of this 8-bit adder. One of the adder might work at a lower frequency, other adder might work at a higher frequency. What it means? It means that although at a logical level both of them are same, but when it will come to implementation, one adder will be completely different from other. So how does DC resolve it by default, or what other steps can we take to resolve such things? So first is the Unify method. This is the simplest of the methods in which the tool is automatic. So that the process of Unify means that each of the copy of the module, so there are multiple instances, each copy is a unique copy. DC will assume each copy is a unique copy. So it will do something which is called unification. Let's see, we'll see it in detail what it means. Second process which we could use is the compile once don't touch method. We'll see what it means. Third is the ungroup method. Let's see in detail. So now in case of Unify, what DC will assume, as soon as it sees U3 and U4 belonging to the same module C, it will make two different copies. It will copy C into C0 and C1, and it will remove C. Now for all practical purposes, what DC did is create separate unique designs. Now this design top does not have any multiple instances. This process is automatic. As soon as you do a compile command, DC will start looking for multiple instances. It will start applying unification. This will remove the original design from memory after it creates a new unique design. This you can only stop this by setting a don't touch command on some design. If the design is don't touch, if you use a command called set don't touch on a particular design, DC will not do anything about the design. So this is again an automatic process, and it is the most desirable process in the sense that you should use this default thing in most of the cases. There are very special cases in which you will use any of these two other techniques, but this is the most famous technique, and it is recommended that you use it almost always. The second is compile once don't touch method. So what it means is that we compile once. That means, let's say a design C has 3 copies. We compile C separately, not as part of the top design. We compile C separately and then read this netlist, read this compiled netlist as part of the top level design. And since this C is already mapped, we set a don't touch on this. So now DC will not do, since we have said don't touch on this, DC will not do anything to it. So we should only do this if the environment around the instances are sufficiently similar. That means all the designs, all the copies of that, all the instances of that design should work on similar frequency or almost same frequency, and even the environment conditions, even the input output specifications are similar. Otherwise, you will see violation in one instance and not see any violation in the other instance. Now let's say you have an 8-bit adder again. One works at 100 MHz, another works at 200 MHz. If you use this approach, then first question is, since you have to synthesize this adder separately, what frequency would you use? Common sense would tell you use 200 MHz. Why? Because a 200 MHz implementation will work at 100 MHz. But now a 200 MHz will have more area than 100 MHz. So in this case, it is not desirable to use the approach. It is desirable to use the Unify approach. But if both the adders work at 100 MHz, you could use this approach. Now, In this method, we compile the design using the environment of one of the instances, and then use the set don't touch command. So these are the steps. We characterize the sub design instance. We should use the characterize command as a second step, as a second iteration, just like we did it for bottom up. It's the same case. We compile the reference sub design. We set don't touch command on these and compile the entire design. For example, let's see, we set the current design to be top. We characterize U2, U3. That means U2/U3 is this design. So we will characterize only one of only one of C3 or C4. We need to characterize only one. So we characterize U3. We set the current design to be C. We did a compile. Obviously, one thing is missing here in this script is the reading this constraint. So we characterize U3, read in the constraint for U3, compile U3. Again, we set the current design to be top, and then set don't touch on U3 and U4, and then we again compile the top level. It might seem a bit confusing at first, but the essence is that one of the sub designs you've already compiled, and you do not want DC to touch it further, to modify it further as part of the top level design. This method, in essence, is very similar to the bottom up command. If you compare these scripts, they are almost same. You use the characterize command, you use the write script command, you compile a sub design, and then you set don't touch on the sub design. So set don't touch part is the only unique part here. Third is the ungroup method. This method is the same as unify method almost, but it will remove the level of hierarchy. So this actually ungroup command is not tied to the unification process. That means ungroup command you can use it to remove the hierarchy at any part of the design. So here what we do is we remove this hierarchy. That is, earlier the design was this. You had U3, U4, U5. Now what we could do is we could ungroup U3 and U4. What it means is that the hierarchy U3 and U4 will be removed. Now if U3 and U4 is removed, all the cells are part of the design is automatically unified, because now the module C does not exist, the design C does not exist, the module boundary C is dissolved. That's what ungroup does. Even you could ungroup U5. If you want, you can ungroup U5. Ungroup is not tied to the unification process. So by doing ungroup, in this particular specific example, we are unifying the design explicitly. So this is one other way of doing that. But again, so ungroup has one more advantage, is that when you ungroup the design, now DC can combine the combination elements of both U3 and U4 and optimize it more effectively. So obviously, the more hierarchy the design has, the more artificial boundaries it has, and the more it will prevent DC to optimize the design further. That is why we say that the design should be logically partitioned in such a manner that it helps DC in optimizing the design and not the other way around. So we saw one example at how to logically partition the design, how to keep the combination logic and the related sequential logic together in the same module. We have already seen that in one of the lectures. Please go back and revise that. So we saw three commands. We saw three methods of resolving multiple instances: unify, compile once, don't touch, ungroup. I would again recommend to use unify. That is the default. You don't have to specify any separate command. The compile command itself will do it for you. Now let's look at the compile command. Compile command has these many options, no map and all that. I would recommend that you go to Dixie shell and read the man page. I would discuss the most famous options that are part of the compile command. So one is the compile effort. This is the map effort. This is called the compile effort. The default option is medium. Design compiler will find a good mapping, but it will not use some of the CPU intensive strategies. So it is medium is appropriate for getting a quick idea of your area and timing. it should be used for most cases. Let's say if you feel that you are still left with some volume, or you feel that you should get a lower area still, you can use a map effort height. Please note, by using map effort height, the run times will increase. They might increase significantly for bigger design. So it will use some of the strategies that it did not use in the medium. So this part is used for some critical design. Right? Other is the incremental compile. Incremental compile tells DC that incremental compile is usually the second pass onwards. That means at first you should run without the incremental compile option. That is, the whole compile process should take place, and then let's say now after the compile is done, the full compile is done. Now you want to think that okay, now I feel that one of the input delays is slightly low. I want to increase the input delay. You can do that and then do an incremental compile. What this will do is incremental compile the portions of the design that are already mapped are exempt from logic level optimization, but it will use a new constraint, new input delay constraint, to fix any timing violation. It will try to fix any timing violation that might arise out of changing a small constraint. Let's say changing an input delay or output delay, and the resulting design will be either same if no improvements can be made, or slightly better in terms of design benefits. There are some cases where designer operators are reselected also. Such a swap, if that swap can improve the optimization cost based on the constraints. So incremental compile is just to see if you made small changes to your constraint, you can use this minus incremental compile option to quickly get an improved netlist if possible. So some figures in, let's say for a design it takes 8 hours to do a full compile. It might take just 1 hour to do an incremental compile. Please do not think that let's say if you want to increase the clock frequency, increasing the clock frequency is not a small change, it's a big change. So in such cases I would recommend go for a full compile. But for small changes such as changing the input delay a bit, or changing the driving cell of some input a bit, or changing the load on the output code, you can use incremental compile. There's one option called boundary optimization. If you enable the boundary optimization, DC will optimize across hierarchical boundaries. This means that a module function in RTL, so the design implementation of a module could now be different from its RTL description of a sub design from the top level design. So in most of the cases where boundary optimization is enabled, it might happen that input or output ports are complemented as a result of this process, and thus the netlist of that sub design will not be functionally equivalent to the RTL. So you should use this carefully. If the output port and input ports are complemented, then the port names are changed. Port names of the sub design, not the top level design, using this variable. Another option is scan. This specifies that the compile command should use the scan flip flops. Now, when you do the first level of compile without scan, now a non-scan flop and a flop with scan functionality has area difference. The one with the scan will have a larger area, somewhat larger area. Now, a non-scan design ultimately will be scanned, right? So for getting the accurate idea of the area figures, you should use this option. Why? Because in this option, DC will start using the scan flip flop. It will not do anything else. It will just use scan flip flop. It will not stitch the scan chains. It will not do anything else. So now this netlist, which has the scan flip flops, will give a better idea of the area, of the actual area, right? So I am assuming that if you are not familiar with scan, it would be good to read some basic stuff on scan. What are the type of scan techniques? What are the basics of DFT? What is the difference between a scan flip flop and a normal flip flop? This course does not focus on DFT. It will assume that you have some basic knowledge of it. So by accounting for the impact of internal scan function from the start, this step will eliminate the need for future reoptimization. So it's a good thing to have. So apart from these options, there are multiple options: exact map, ungroup all, and so on. You could read more about it. There will be examples. So as and when we proceed in this course, we will see some of the examples, and then I'll explain the option. This option is very important, very interesting. Gate clock. So I'll have a couple of lectures on power. I'll discuss this gate clock during the power discussion. So this gate clock is used to save power, save dynamic power. We'll see how, and we'll see what this option does. So so this is so we saw the different compile strategies: top down, bottom up. We saw how to resolve multiple instances using the unit map process or compile once, send this, don't touch. We saw the ungroup command. Then we saw the actual compile command. So there are two commands, as I said before: compile and compile extra. In this lecture, we have seen the compile command. In unit 4, we'll see the compile extra command. You might not use compile extra command, but the compile extra has a lot of advanced synthesis features. So between unit 4 and unit 5, unit 3 and unit 4, just before we start unit 4, I would recommend you to be comfortable with this command. So you can understand the advanced features only if you understand the basic features first. So this compile command has a lot of basic features. Read about this compile command, try out different variations, see what each of this option does to your netlist, does to your optimization. Read more about it. And when we start unit 4, it will help you to understand the compile extra command and some of the advanced synthesis features a lot better. Thank you.